So in the last class, we had started on SCRs and we had also started looking at how to analyze the device. As I told you, SCRs basically are 4-layer devices. So I'm going to have PN, PN. This is the way it is going to be. So which I said can be looked upon as a PNP transistor. So this is a PNP transistor which is connected to an NPN transistor. So if I say that this is P, this is N and this is P and this is going to be N, P, N, this particular P is connected to this P like this, and similarly this N is connected to this N like this, and we said that this is anode, this is cathode and this is the gate terminal, right? So this is the way we are going to visualize an SCR, which is a 4-layer device basically. So if we are looking at these two transistors, when I am applying positive to anode and negative to cathode, right? You can see that this transistor, we have, this is the emitter. So emitter base junction is forward biased. Similarly here also emitter base junction is forward biased. N is negative and P is not having any potential as such. So both these will be forward biased, but if you look at the N of the collector here, either this or this, that particular junction is reverse biased because we are not applying any voltage at all. So they are going to be essentially reverse biased. So if I apply a positive voltage here to the gate with respect to cathode, then what is going to happen is I am pushing a gate current here. So if I am pushing a gate current here, I am going to have a larger collector current as per the transistor operation, because beta times IB, beta is the amplification factor, current amplification factor. So I am going to have a large current flowing through the collector. So that is going to flow into the base of the other transistor, because of which again I am going to have a larger collector current here. So it is essentially feeding into each other, and even for a very, very small amount of gate bias, we are going to see that eventually both the transistors are driven into saturation. Both of them are conducting with very, very minimal voltage drop across themselves. That's what we mean by saturation. So once I just give a pulse, I have already started the conduction process, because of which if I remove the gate pulse, no difference will it make to the device. So the device will be latched into conduction and I don't have to do anything to keep it still in conduction mode. So this can be visualized as a positive point or a negative point, because if I give a gate pulse and if it is latched into conduction, well and good, I don't have to give any gate signal at all. So my gate signals, circuits, methodology, whatever is the functionality, that is minimized. No problem at all. I will not have any losses and so on and so forth. But if I want to turn it off, it is not going to be easy. If I am, for example, talking about an inverter, I had shown this inverter earlier also when I was talking about RL load and feedback diode. So this is an inverter circuit with a DC voltage as the input and AC voltage as the output. So this is going to be my inverter circuit. So if I say that this 1 and 1 dash correspond to positive half cycle when the current is flowing in this direction. Okay, if I have 1 and 1 dash turned on, the current is going to flow in a particular direction. If I am going to have 2 and 2 dash turned on, 2 and 2 dash turned on, I am going to have the current in the opposite direction with 2 and 2 dash turned on, whereas this is going to be for 1 and 1 dash turned on, right? But By chance, if I am not able to turn off 1 and 1 dash, if I am not able to turn off 1 and 1 dash, but I have turned on 2 and 2 dash inadvertently, without knowing, then what will happen is, both these will conduct together, both these will conduct together. So you are looking at a dead short circuit across the DC supply. So extremely large currents are going to flow in case I am not able to turn off 1 and 1 dash and I have turned on 2 and 2 dash. That kind of a condition is generally known as shoot through. In an inverter, we call that condition as shoot through, in which case I am essentially going to have, a short circuit right across the supply. So this condition is definitely a very dangerous condition because the battery is essentially like an infinite source. So it will be able to circulate a very, very large current, and if these devices are not able to withstand that current, they are going to conk out. So if I have 1 and 1 dash and 2 and 2 dash as thyristors, they are all SCRs or thyristors, then I'm not going to be able to turn them off very easily. So whenever I have to use a thyristor in a DC circuit with the input as DC, I have to have some additional circuits to make sure that they are turned off well in time. Whenever I want to turn them off, I have to use this additional circuitry to make sure that they are turned off well in time. Those additional circuitry which are meant for turning off the thyristors or SCRs, these are generally known as commutation circuits. Commutation basically stands for current transfer. So I'm going to transfer the current from one set of devices to the other set of devices. So I call these circuits which are able to turn off one set of devices and transfer the current over to another set of devices, I call them as commutation circuit. Right? So if I look at actually the types of thyristors or SCRs, there are mainly 3 types of SCRs that are available in the market. The first and foremost one, we call them as power frequency thyristor or converter grade thyristor. Converter grade thyristor is generally used for rectification. It is used for rectification. So converter and rectifier again are used interchangeably. They are kind of synonymous. So converter grade thyristors are generally used for rectifier operation, whereas there are inverter grade thyristors. Inverter grade thyristors are generally used in those circuits where I may do DC to AC conversion. So depending upon how quickly I am going to turn on or turn off the devices, I am going to get the frequency output modified accordingly. If I do 1 1 dash and 2 2 dash alternately turning on very quickly, then the frequency of the output AC will be large. If I am doing it slowly, the frequency of the output AC will be small. So if I want to go for higher and higher frequencies, then the normal converter grade thyristors, which are normally slow, they are much slower. Turning on and turning off takes a longer time. So inverter grade thyristors can be used in those places. So these will be faster normally, whereas this will be generally slower. What I mean is turn on and turn off. This will be generally pretty slow for the converter grade thyristor, whereas it will be fast for the inverter grade thyristor. And normally we give a gate current in any of these devices to turn on. Sometimes we may use light to activate, so that photoelectric effect kind of thing we will use, and that will emit some electrons, because of which I will have the conduction possible. So the third one is LASER. LASER is light activated silicon controlled rectifier. So LASCR is, those devices will be activated basically by light. So these are light activated SCRs. So these are mainly the three types of devices that are available in the market if you go under the category of SCR. So if you actually look at the ratings, SCR ratings are really large that are available in the market, are very, very large. In fact, there are some companies, in fact our BHEL produces some SCRs, in Mitsubishi produces, Fuji, Toshiba, Infineon Technologies, all these things, International Rectifiers in USA, all these things produce, SCRs. And Mitsubishi generally has a very, very high rating, so also is Infineon. Mitsubishi rating is of the order of about 6.5 to 8 kilovolts along with about 4 to 5 kiloamperes. Very, very large rated SCRs are available from Mitsubishi. But mostly the highest grade SCR, highest power rated SCR will be converter grade. Inverter grade, because they have to be turned on and turned off very quickly, which means huge number of charge carriers. They have to be swept out. It takes longer. So generally inverter grade thyristors will be available only at lower rating. This may be available only at lower rating, whereas this will be available at higher ratings. So these are, some of the characteristics of thyristors when we look at the different types. Now let us try to take a look at how to fire a thyristor or how to trigger a thyristor. How are we going to trigger an SCR? What we mean by triggering or firing is, we are going to turn it on from off condition. It is going to be pushed into on condition. That's what we are trying to do. So invariably, thyristor, by the way, the symbol is somewhat like this. I'm going to have anode here, cathode here, and gate terminal is generally specified like this. So to this gate, I'll have to give a small amount of positive bias. Then it would be able to conduct, right? But if I look at the current amplification in this case, Ig versus I anode, if I try to look at it, generally in an SCR it is 1:1000 or more. So if it is like 1000 ampere thyristor, 1 ampere of current would do in the gate for it to be triggered. So obviously the circuit that is connected here is going to be microelectronic circuit, whereas what is connected here will be power electronic circuit or high power circuit. So as I told you earlier, it is essential for us to have isolation between microelectronic circuit and power electronic circuit, because if something goes wrong in the power side, huge amount of current will flow into electronic side and it will not be able to withstand. So normally the grounds will be isolated. The grounds will not be connected together. So how do we really, isolate the ground of the SCR's gate versus anode? That's what we'll have to check. So let us say I have probably gotten some pulse. Something like this. This is the pulse that I want to give it to the thyristor. Okay? If I give a pulse directly, and if I am planning to use a transformer for isolation, then the transformer will saturate. Transformer is not supposed to carry DC. So if I am trying to isolate the gate circuit with that of anode circuit with the help of a transformer, I would like to convert this pulse into some kind of smaller duration pulses. So what we can think of is like a clock in your computer or microprocessor. I can have a clock and this high frequency pulse and the normal pulse. Both of them can be given to an AND circuit, AND gate. So if I do that, whenever I'm going to have this pulse, I'm going to get essentially the output of this to be, all here it will be 0, and then I'm going to have some pulses like this. This is how the pulses will be, right? This will be the output of the high frequency ANDed circuits. So this now, if I can give it to a transformer, in all probability the transformer will not saturate provided I give ample time here for defluxing, or whatever is the flux that has been accumulated in the transformer winding, it should have enough sufficient time to kind of, get rid of that flux, right? So this particular thing, whatever is the high frequency, so this is HF pulses and this is HF ANDed pulses. So high frequency ANDed pulse, now this may be only of 5 volts and a few microamperes in all probability. If it is a 1000 ampere thyristor, I said that I will need 1 ampere to fire it. So I need to amplify it. So there has to be a current amplification circuit in between. So whatever is the output here, this goes to current amplification stage. So the current amplification stage can be a simple common emitter amplifier, like what you have seen in transistor. Maybe you studied this in 12th class. After that, I don't know whether you guys have again studied transistor. ELL 100 little bit was introduced to you in the form of transistor, but we will have to have a current amplification stage. So this current amplification stage normally will be an NPN transistor. So whatever is this signal, this we are going to give it to the gate, and here is my transistor. So I can imagine as though the transformer is here, right? The transformer primary I have shown, and I necessarily have to have another secondary. So if we have seen big transformer in terms of megavolt ampere and so on, this will be 1 volt ampere or maybe maximum 10 volt ampere. That's it, nothing more than that. It is going to be a very, very small sized transformer. It will still be ion core normally. It will be an ion core transformer, and generally gate has to get positive and cathode has to get negative when I am giving the gate pulses. So generally, if I say that this is my VCC, which is actually plus, obviously this corresponds to minus. So this will go to cathode, and in all probability I may put a diode as well to make sure that no negative pulses go into the gate, because it can be detrimental to the gate. So we will normally have a diode, and here is where I will have the gate connected. And here, when I am having the current during the pulse being in high stage, the current cannot be abruptly brought down to 0. So normally I may have a freewheeling diode here. There will be a freewheeling diode here, right? So much so for the triggering circuit of a thyristor or SCR. So you are starting from the pulses. You normally AND it with high frequency to make sure that the transformer which I am going to use here does not saturate, right? After high frequency ANDing, I necessarily need to amplify it, because in all probability SCR will require a higher current. So this amplification stage itself will have the pulse transformer connected in the collector of the transistor, so that I have complete isolation. Please note that this cathode, if I call it as the ground of the power circuit, here is the ground of the electronic circuit. This ground will be the same as that of the pulses ground and AND circuit ground and so on and so forth. So the electronic ground is here. So this is electronic ground. This is electronic ground, whereas this will be power ground. So the two grounds will be completely isolated from each other. And I am able to give this kind of an isolation with a transformer because it is an SCR. Once I give a pulse, it will start conducting. So even if I bring down, the voltage, still it will continue to conduct. It's not going to shy away from conducting. That is the major advantage of having an SCR, and we can have basically isolation with the help of a transformer, which we will see eventually that in BJTs or MOSFETs or IGBTs, we will not be able to do, because there, if you give a base pulse, the base pulse has to be in high condition continuously for the device to conduct. If the base pulse is not in high condition, it will come from on state to off state, and we don't want, in all probability, our device to go from on state to off state. Most of the times we fire it with multiple number of pulses, because by chance if it doesn't fire here, it can at least fire here. By chance if it misses these two, it can at least fire in the third, and so on. Okay? Because invariably SCRs are used with AC supply. And at what point really the alternating current goes from the positive half cycle to negative half cycle, or negative half cycle to positive half cycle, we may not be sure. So we want to make sure that we give it ample chance for conduction. That's the reason why we will repeatedly give the pulses, so that we give it ample chance to get into conduction. Right? So SCRs, if I look at, triggering is pretty simple. It's not too involved, because all you need is a high frequency ANDing and another amplifier and a pulse transformer, nothing more than that. But commutation is going to be a little more difficult, but before that we'll also look at series and parallel operation. I don't think I need to really expand upon that much, because we had already seen for diode a similar situation happens for SCRs also. So series and parallel operation of SCR is very, very common. Very, very commonly we do the series and parallel operation. Yes. See, you are not doing the power amplification. This is even power amplifier. I should not say only current amplification. It is actually power amplifier. Because what I get from here may be 5 volts. And what I get from here may be 15 volts. And what I get from here may be milliamperes or microamperes. But what I get from here will be of the order of amperes. So I'm not only amplifying only the current, I'm also amplifying the overall power. And for that I'm drawing the power from VCC. So VCC is supplying the power for me to amplify the current pulse. Whereas in this case, if I just use a transformer, either you will amplify the voltage or you will amplify the current. You cannot amplify the power. The power is invariant, right, from the primary side to secondary side. So that's the reason why we use the transformer only for isolation, not for amplification. Right? Have I answered your question? See, basically it is not just the current alone. We say that gate has to be forward biased. So forward biasing voltage and the gate current, both will be specified for a device. In fact, if I look at the device specification, normally if I just say how the device specifications are given, normally what they will give is the forward blocking voltage, how much voltage it can block in the forward condition, right? The second thing they will give is what is the reverse breakdown voltage, right? And again, even in the reverse breakdown voltage, there will be two different kinds of categories they will give. Normal reverse breakdown voltage and repeated reverse breakdown voltage. If I just apply only 7 kilovolts, this device may be able to withstand. But if I repeatedly apply 7 kilovolts, it may conk out. Because I am putting it under stress repeatedly. So it will conk out. So repeated reverse voltage and just once a reverse voltage or the peak reverse voltage that I can subject it to. So these are two categories normally they will give. Then apart from that, they'll also give what is IRMS it can withstand. Then they will give what is I peak it can withstand. Any device, right? And then they will say what is VGK that is needed for triggering the device. Then apart from that, they'll also say how much is IG, how much is the gate current that is needed. Then there is one more thing which will be coming out as turn on time. How long it takes for the device to come into on condition. After I give the gate pulse, does it immediately come on or does it take a little longer? So that is turn on time. Then there will also be turn off time, because turn off is not easy. We are going to look at that also, but turn off is going to be difficult. So which means if the recombination takes 50 microsecond, 100 microsecond, am I enabling the device to completely recombine? So that is essentially specifying what is the turn off time. Apart from that, they'll also give what is di by dt and dv by dt the device can withstand. How much is the di by dt the device can withstand? If I try to go beyond that, the device might break down. Similarly, dv by dt, because while turning on, I'm going to have from a large voltage, it will come down to 0 voltage or very low voltage. Similarly, when I'm turning off, it will go from a very small voltage suddenly to a large voltage, right? So in both the cases, it should be able to withstand. So dv by dt limits are generally given. And as we had done in series and parallel operation of the diode, here also I can have series operation of thyristor like this with large resistances in parallel. Similarly, parallel operation I can do for two thyristors with small resistances in series when I want to share a larger current I. Right? Here it is sharing a larger voltage V among the two devices. Right? Now this is very, very commonly used in high voltage DC transmission systems. I don't know whether you guys have heard of high voltage DC transmission system. In high voltage DC transmission system, what happens is, if I am having a generator, I'm just showing this as though it is a single phase generator. We call it a single line diagram. It is 3 phase, but I will show only one line at a time. Every line indicates 3 phases basically. So this is my generator, and I'm going to have basically a transformer which will step up. Maybe the generator will generate only 11 kilovolt or 12 kilovolt or whatever. From this, it is going to be generally stepped up to 400 kV. The transmission voltages are very, very large because we want to bring down the current. For the same power, we want to bring down the current. But the generator has a limitation of what is the maximum voltage it can withstand. Otherwise, you are going to have very thick insulation inside the machine. And in all probability, I will not be able to put such thick insulation inside the machine. That's the reason why we are having 11 kilovolts or smaller. Sometimes we will go up till 20 kilovolts, nothing more than that. So there is a limitation of generating voltages because of the insulation that is being used in the machine. Whereas the transmission voltages are generally chosen to be much higher because I would like to bring down the current. That is the reason. Right. So this has now brought down the current, and then from here it is going to go and it is going to get distributed, transmitted and distributed all over the country, for example. Right. But when I distribute it or transmit it, These are 3 conductors. Please note all these are at least 3 conductors. And apart from that, I may have a neutral also, because if it is actually the generator star connected, I may ground the neutral as well. So I will have 4 conductors coming out normally. So if I have 4 conductors coming out, and when I have 2000 kilometers being, spanned, maybe from northeast region to Gujarat. So obviously, I will have 4 conductors going all the way through these 2000 kilometers, which is definitely going to be extremely costly. So I can't afford to always have AC transmission. AC transmission comes in handy because of the transformer. It can step up and step down the voltages, which is very, very good. That's the reason why Tesla won the war of power, right? When you compare Edison and Tesla, Edison actually lost the war of electricity or power because he was always arguing for DC, whereas Tesla was arguing for AC, and Tesla was hired by Westinghouse, and Westinghouse is the one who ventured into AC transmission, right? So this AC transmission becomes costly when I am talking about long distances. So now that we have rectifiers and so on and so forth, everything is available with the power electronic converters. So what is being done normally is, whatever is available in the form of 3-phase, this is actually connected to a rectifier. And the rectifier obviously has to withstand 400 multiplied by root 2 kV, because 400 kV is RMS. So 400 times root 2, each of the devices have to withstand, and I have to put a factor of safety in all probability 1.25 or 1.2, so it is going to be way too high. There are no devices available for 400 kV multiplied by root 2 multiplied by 1.2 or whatever. That's not going to be possible. So we use lot of thyristors in series. Normally that's what we do. So whenever I'm talking about this rectifier, this is going to essentially use large number of SCRs in series. This is going to have large number of SCRs in series. Now the rectifier has rectified the voltage, so I'm going to have a plus and I'm going to have a minus. Right? Now there are only 2 conductors. I can take it to extremely large distances. I'll save on copper. Instead of 4 conductors, R, Y, B and neutral, now I have 2 conductors. In fact, in some of the cases, this will be, return will be ground. In some cases, return may be ground, which means I have only 1 conductor, right? So compared to 4 conductors, if I can bring down the cost by using only 1 conductor, obviously it makes better sense. So that is the reason why many of the large distance transmissions now are being thought about to be done with HVDC, high voltage DC transmission. So high voltage DC transmission is applied in many of the cases where I have to transfer electricity over very, very long distances, so that I will be able to save on copper. That is one advantage. Another advantage is, let us say I have 50 hertz here. Maybe I want to tie it up to some other system which is having maybe 49 hertz on the other side. So I will have an inverter here. An inverter I can fire at my own will and wish. Not a problem. Fire it at 49 hertz. Ho gaya kaam. Right? So I can directly connect this to the 49 hertz source. And in between, of course, I may have several loads connected. Many loads may be connected directly to DC, maybe to AC, and so on and so forth. So high voltage DC transmission systems invariably use light activated SCRs. They use light activated SCRs because light definitely is no way connected to electricity. I don't have to worry so much about isolation and so on. And it is a very, very high voltage and high power device. So inherently, if there is isolation, nothing like it. So I may use several LASCRs in series. I may not have to use them in parallel because I may have 400 kilovolts and maybe 4000 amperes. That is good enough, or 2000 amperes. And one SCR can carry very easily 2000 ampere, not a problem. So most of the times what we see in HVDC transmission system is series connected SCRs. Hardly ever we see parallel connected SCRs. So we'll have rectifier. For every device in the rectifier, there will be a string of SCRs, many of them connected in series. Of course, with parallel resistances, protection system. So the SCR may be only this much, but all the paraphernalia which is adding will be too big generally, and the heat sink and so on and so forth. So many things will be there. So this is typically the case when we talk about series operation and parallel operation of SCRs. Now let us go over to the commutation circuit. What we mean by commutation is to turn off an SCR circuit. How are we going to turn off a circuit? I'm going to take an example and explain it so that you would be able to get an idea of how an SCR is turned off. So let us say I have a chopper circuit. Again, that is one of the simplest circuits, so I'm going to take a chopper. I'm having an SCR. I'm calling this as main SCR, M. Okay? And this is connected to the DC motor drive. Maybe I'm going to feed a DC motor drive with a chopper. The chopper consists of basically a switch, nothing more than that, right? A DC voltage source and a switch. Now I'm going to have a freewheeling diode. Of course, this we already said it is essential. If we don't have a freewheeling diode, it is going to be a problem because the current will be abruptly interrupted. L di by dt will be very large. Thyristor will conk out. So I don't want that to happen. And motor by default will have some inductance. Can't help it. So that's the reason why I'm putting a freewheeling diode. So this is a freewheeling diode. When I turn on this main thyristor or main SCR, I'm going to have the power supply given to my motor. But I would like to turn it off after some time so that the average voltage becomes less. I want to have a control over the voltage, right? That's why I am employing a switch. So I want probably this to be on for some time, off for some time, again on for some time, off for some time, and so on. This is how it is going to be. So this is T on and this is going to be T off. And this entire thing is going to be the period of the chopper, T. This is how it is going to be, right? So the average value of voltage, I told you already that whatever is the on time, correspondingly it is going to have T on divided by capital T, whatever is the period. So multiplied by the applied voltage. That is going to be the average voltage, right? This is how it is going to be. So I have to turn this off at this point. If I don't turn it off at this point, it is going to be difficult. I can't really get the average voltage to be less than whatever is the input voltage. So to turn it off, had it been a transistor or something, I could have just removed the base drive. If I remove the base drive, it will go off, simply. If it's a FET or whatever it is, the moment I remove the drive, it will go off. But in this case, it is not going to go off. We said that once those two transistors are driven into conduction, they will not come back. That's the problem. So for that, we have to have some auxiliary circuits which are known as commutation circuit. A typical commutation circuit I am going to show, right? So these are all part of commutation circuit, what I am showing in red. So many things. This is a capacitor, this is an auxiliary thyristor, then I'm going to have an inductor, I'm going to have a diode and so on and so forth. So many things are added to make sure that this particular device goes off. So whatever I have shown in red, the entire thing corresponds to commutation circuit. That corresponds to commutation circuit. So let me try to explain how this works. Okay?
So as I had told you earlier, the main thyristor M is actually going to give the power to the DC motor drive, and it has to be turned off at the end of T on. So if I talk about the entire thing as a chopper circuit which is feeding the DC motor drive, for T on it is going to be on, and for rest of the period it is going to be off. Again for T on it is going to be on, and so on. So this entire period is the period of the chopper. So 1 by T is equal to F, which is the frequency of the chopper. Okay. So I am going to have M fired at this point, and whenever I want to turn that M off, I am going to fire the auxiliary thyristor at this point. Okay. As I told you, all that is drawn in this red color, all these things are part of the commutation circuit. This is the capacitance C. Now let us say the capacitance is already pre-charged to a voltage like this. This could have been done by having an auxiliary resistor and a switch which can be closed for a short while until the capacitance charges to this plus and minus with VDC. The voltage is VDC currently. Okay. Now whenever I want to turn off M, I am going to fire A. So the moment I fire A, there are two currents that will be flowing through M. One is directly from DC source through M to the DC motor. This is one of the currents, and the second current is going to be the capacitance itself is going to discharge. So you can look at the discharging path somewhat like this. This is going to be the discharging path. So I will have C, then M, then I am going to have the diode D1, then I am going to have inductance L back to C. So if I assume that L and C are ideal, it is going to have an oscillation, LC oscillation through this circuit. So if I try to look at the voltage, I am going to actually see that the voltage will reverse like this. It is starting from plus VDC and it will go to minus VDC. So this is essentially the capacitor voltage. So VC I am drawing like this. At the same time, if I try to look at the current would have reached the peak when the voltage is actually at the 0 point, and it is going to reach 0 when the voltage is at the negative peak point, that is when it is at negative peak. So this is going to be the capacitance current waveform, or is this the same as the diode current waveform. So this oscillation time will be equal to pi root LC. All of you know this definitely, right? In an LC circuit, pi root LC is going to be the half cycle time. So within pi root LC, this would have reversed its charge. So you would see that now this has become plus and this has become minus. The moment I am going to have this has become plus and this has become minus, now this is ready to commutate the main thyristor at any point in time. So I am going to now fire this auxiliary thyristor. So this is essentially when M is fired, whereas when A is fired after pi root LC elapsed from M, or even more than that, at that point I am going to have essentially the circuit somewhat like this. This is the capacitor which is having plus here and minus here, right? This is minus, and I am having the main thyristor here, and I have an auxiliary thyristor which is working like a short circuit. You can very clearly see that the plus is connected here and the minus is connected here, which is going to force a huge current in the opposite direction. The resistance is literally negligible because the current is having, a huge reverse component. right. So, essentially that cannot be allowed by the thyristor. So, M is going to go off. So, M goes off instantaneously. So, you can say because M goes off instantaneously, we call this as hard commutation. If you are allowing the reverse current to rise slowly, then you will call that as soft commutation. Soft commutation is such a case where you are going to make the reverse current rise slowly. If I allow reverse current to rise slowly, right. In that case, we will call it as soft commutation, but this is very clearly hard commutation. Once the commutation takes place, this M is not going to conduct anymore. When M is not conducting anymore, now the path for the current will be through the capacitance like this, through the auxiliary thyristor and through the freewheeling diode, through the DC motor drive like this. That will happen until the capacitance charges to plus and minus like this, fully to VDC, after which the capacitance will act like an open circuit. So, now the freewheeling diode will take place. I can actually say freewheeling diode should have been there in the circuit because DC motor has at least some amount of inductance. Now, you can see that the current will flow like this, it is just freewheeling. So, in this particular case, you can see there are totally 3 modes. One is first when M is fired to supply the motor drive. Simultaneously, you are going to have the capacitance reversing its charge, okay, which means this will need at least pi root LC as the time that is needed for the main thyristor to be on. So, this is the minimum on time. I cannot have less on time than this. This is the minimum on time. The second portion is when M has to be commutated or turned off. Under that condition, I am essentially going to fire A. When A is fired, I am going to have essentially instantaneously, right, instantly I am going to have M is turned off because of very high current flowing in the opposite direction. And after this, I am going to see that auxiliary thyristor, that is the auxiliary SCR, allows capacitance to be charged back to VDC. So, it will be ready for the next cycle of operation. After this, freewheeling diode takes over. So, basically this circuit is designed based on 2 things. One is this minimum T on, which is pi root LC. Another one is you are going to have basically I load or I armature of the DC motor might have been given already. This is the load condition. So, you can say C delta V equal to I delta T, right. And if I actually look at it, the capacitance voltage is literally going from plus VDC to 0 to minus VDC. This is how it is transferring, right. So, which means whenever it is actually having the voltage with the polarity plus here and minus here, then this main thyristor is going to be reverse biased. Only if it is reverse biased, it is going to be turned off properly. So, how long will it be reverse biased? Until this voltage becomes 0. So, I can say delta V in this case happens to be VDC, C is the capacitance value, and I am going to have I as the armature current, whatever is the armature current, multiplied by delta T. So, how long does it take to reverse is governed by the capacitance, what is the DC voltage and what is the load current.